Welcome to Investigation 3.2. In this investigation, we were talking about distance, speed, and time. So our focus for this particular investigation is what examples using distance, speed, and time show one variable inversely related to another. If we remember from the last investigation, inverse variation deals with this whole concept of one aspect of the graph changing different or opposite as the other one increases or decreases. So if one side of that rectangle increases, the other side of the rectangle will have to decrease to compensate to keep the area the same. And we end up with a situation that looks a lot like this. So it has that nice little like water slide sort of slope going on. We have that cool little like perfect sled hill that is created with an inverse relationship. So let's look at a few examples that we can try to sink our teeth into. So we have Mr. McClellan, our vice principal, our assistant principal. So Mr. McClellan, the assistant principal, he regularly travels to Billings to visit his wife's family. The distance between his house in Bozeman and his in-laws' home in Billings is exactly 120 miles. Use the following data in the table to determine if his speed is inversely related to the time needed to travel to Billings. So we have 4 different scenarios. One day, bright and sunny, clear roads, it takes him 2 hours. Another day, he hit a deer and he had to call for a tow truck, so it took 4.5 hours. Another time he was speeding because he was late for dinner with his family, and that took 80 minutes. So it looks like we're going to have to look at our units for that one. And then last, he was training for an Ironman, so he biked there. Crazy man. All right, so let's figure out the speed for these various scenarios. So let's add on to our table, and we are going to add speed to this table. So if we had 120 miles, and we are looking for how many hours, or his speed if it takes 2 hours, we know speed is essentially equal to distance divided by time. So we need to do 120 and divide it by 2, and we'd get 60. So we have 60 miles per hour for that case. He then has also done this crazy thing of hitting a deer. All of us understand that. There's deer all over in Montana. So we have 120 miles, and we're dividing that by 4.5 hours. Now we all know that if he hits a deer, he's not consistently driving the whole time. He's essentially stopped and stuck on the side of the road for a while his radiator fluid leaks out or whatever it may be. But we can figure out an average speed. And so 120 divided by 4.5 is 26.6 repeating miles. So we can add that now to our table, 26.6 repeating miles per hour. Let's do a couple more. Oops, I can't erase anymore. Let's do a couple more, and we have 80 minutes. So that's kind of tricky, 80 minutes. If we're looking at 80 minutes, we need to convert that into hours because we're looking for miles per hour, not miles per minute. 80 minutes is essentially 1 hour and 20 minutes. Now let's think, how can we convert that 20 minutes into hours? Well, we know there's 20 minutes in 1 hour, which is 60 minutes. So 20 over 60, let's do a little math. We need to reduce this, or we need to simplify it, so we get 2 over 6, which is 1/3. So essentially 1.3 hours, or 1.3 repeating, 4/3 of an hour. So let's do a little bit of math now. Let's use that ratio, use that fraction that we just developed, and do 120 divided by 1.3 hours. And if we do that, we get 90 miles per hour. Mr. McClellan, you need to slow down, slow the roll, man. 90 miles per hour. He is lucky he didn't get taken over by the cops. Then he was training for an Ironman and he biked. Hopefully there wasn't a headwind, but looking at the 12 hours and looking at 120 miles, there probably was. But 120 divided by 12, that'll get us a solid 10 miles per hour. So looking at this information, now let's take it to a graph and let's turn it into a graph. So let's move over here, get ourselves a little graph. So just 1 minute, magic will happen. So there we go, we have our graph now. So we need to look at time versus speed. And as what I've noticed with these inverse relationships, yes, it's important to pay attention to the independent versus dependent variable, and our independent variable at this point in time is our time, and our speed is dependent upon that. In all reality, we know that what we looked at with our rectangles is we saw that it became reflected after a while. So it really doesn't matter if we put speed or time on the x-axis or the y-axis. However, convention tells us that typically time is on the x-axis and speed would then be on the y-axis. So let's do a little thinking about our scale here. Along for time, we have 12 hours, so we'll just do every 1 unit is essentially our scale, and speed we have up to 90, and we have 20 along the side, so we'll maybe say every 10, or every unit is 10. So I'm going to do a little math magic. Hold on a second. Alright, so I actually decided to go by 5s on that upper portion. Either way, we have speed and time, so now we just need to graph this stuff. So let's graph it in red so we can really see it stand out. If we have 2 hours, he was going about 60 miles per hour. So we have a little dot there. He was in 4.5 hours, he went 26.6 miles per hour. So we have a little dot right in there. Oops, I did 4 hours, not 4.5, sorry. 4.5. There we go, that's a little better, At 1.3 hours repeating, 1.3, he went 90 miles per hour, so the crazy man was going super fast. And that's a little too off for my perfectionist style. Oh my goodness, I'm ridiculous. All right, whatever. And then at 12 hours, he went 10 miles per hour. So we have, yet again, a little mess. So there is our graph. And as we can see, this is not a linear relationship. It's not a straight line. It looks like it's more of one of those inverse relationships. So we're starting to see things develop in that same sort of way, that inverse way. So we can say essentially that speed with fixed distance with a fixed distance is inversely related. Oops, that's not how you spell related. That's how you spell rat. Related to time. So speed with a fixed distance is inversely related to time. Let's look at a situation that maybe isn't so inversely related. So now we have Mrs. McClellan. Mrs. McClellan is not as adventurous, especially when their daughter is in the car. She always drives 55 miles per hour on the frontage roads, especially when the weather is nice. How is her speed related to the distance she travels and the time it takes her to drive to her parents' home? So looking at this, the best thing that I can think that we need to do is essentially make a table. And our table is going to be pretty consistent when it comes to speed, but we really need to look at distance and time. Actually, I'm going to do time and distance because the time is dictating how far we're going. So if we went 1 hour, we could say that she drove 55 miles. If she drove for 2 hours, she's at 110, almost to Billings. If she drove 3 hours, she's past Billings and gone 165 miles. Maybe she's going and visiting a cousin or something. If she's at 4 hours, she's at 220 miles. We can continue this on forever and figure out how far she's going in 10 hours, and we could say 550 miles. Regardless, we're seeing a very interesting trend. What I'm seeing in this trend is the following. We're pretty used to linear equations already. So with linear equations, we're able to see patterns in various tables that we create and see how things change. So if we're looking at the pattern, if we look at the time, it is increasing by 1 hour each time. which is kind of cool. And if we look at their distance, it's increasing by 55 each time. So in this case, we're looking at a situation that is linear. It's not inverse. It's not an inverse relationship because we can see that continuous pattern. If we were looking at the other pattern that we were using with Mr. McClellan, we wouldn't find a constant change in our speed in our time in comparison to the speed. They would end up being all over the place and kind of crazy. So instead, we can look at this one and we can see that there is a clear linear relationship. Let's prove it to ourselves with a little graphing, however. Let me get a graph out here, just one moment. So here is our little graph. I'm going to zoom in a little bit so that way we can just look at our table and this graph at one time. So as we know, time is typically on the x-axis and distance will be on the y-axis. This is also because time is very definitely our independent variable, and our distance is our dependent variable. It's dependent upon the time. I'm going to add a little scale in here. So again, math magic. Wait a second. So there we go. We have a little bit of a scale. It's a little off, but whatever, we can deal with it. So we can look at this. We have time at 1 hour. Well, first of all, we could say at 0 hours, she's starting from home. She's right there at home. At 1 hour, she's at 55 miles. So let's add that in there. She's about right in there. At 2 hours, she's at 110. So she's right there. At 3 hours, she's at 165. So somewhere in there. And at 4 hours, she's at 220. So we can sort of eyeball that one. It's going to be like up here somewhere. So looking at that, it is very, very clearly a linear relationship. And we can sort of hit all of those dots in a nice straight line. That was actually pretty good. So in this case, we can say that speed, when fixed, is a linear relationship for distance and time. So looking at that, we essentially, if speed is fixed, we can look at distance and time and see how they change. However, when we have a situation when distance is fixed and speed could change however it feels like, our time is inversely related to that. So we'd end up with this crazy water slide of a graph. So play around with the homework for investigation 3.2. If you have any questions, as always, please ask in class tomorrow, and I will see you later. Ciao.